Hello, good afternoon, everybody. We continue our adventure with graph algebras. I'm afraid that today I have to apologize in a completely the same way as I apologized a week ago. So I'm again a bit of a zombie because I spent almost the whole night proving a new theorem for you. But I'm very happy. This time it's not just a proposition, it's in fact a theorem. And as you can guess, this is a theorem about covariance of a construction of Leavitt path algebras from graphs. So of course, this is a very well-known fact if you take very simple morphisms in your category. But here the name of the game is to take maximally general morphisms in the category of graphs that yet allow you to maintain covariance of the Leavitt path algebra construction. So in other words, and this I believe is a completely new result, which I think is more difficult than what we proved for conpath algebras a week ago. And here the main difficulty is actually to fine-tune assumptions of your theorem. It was really tough. It took me much of a night to figure it out, because if you try to do it naively, it just doesn't work, or you are very happy, all right, now I've got it, and then you have a counterexample. Then you think again, okay, maybe this way, and again you have a counterexample. So somehow figuring out what you need to assume to prove a theorem, that's the hard part. And once you do it well, this is mostly a matter of bookkeeping and how to write it down formally and rigorously to see that everything rock and rolls. But before we pass to this new theorem of the day, I'd like to study some examples that explain our proposition about the covariance of a construction of compact algebras. And a key reason for studying these examples is to distinguish the following three cases. So what we assumed, the M condition, was saying that if I have an edge, so I have E1 and E2 in E1. Okay, so my standing assumption is that I have my graph path homomorphism of graphs. So I have a map from F to E, from finite paths in E into finite paths in F. Okay, so let me discuss these three different assumptions. So by my examples, I'm going to show you that these assumptions are really different. So our M condition was the following. If we have that f of E1 is equal to f of E2, it must follow, sorry, no, not equal. This will be just injectivity. Is less or equal than f of E2. So none of these paths extends the other. Then it implies that E1 is equal to E2. Okay. Then we have a condition in a published paper that says that if I take any paths, say alpha, beta, finite paths in E, then I want to have this implication that f of alpha is less than equal than f of beta. This implies that alpha is less or equal than beta. And finally, we just have plain injectivity, which says that on edges, which says that if I have f of E1 equal to f of E2, then this implies that E1 is equal to E2. Okay, so you can obviously see that the left assumption is weaker than the right assumption. You have, of course, if the condition M is satisfied, then this injectivity on edges condition is satisfied. All right, and that's because V equality is a special part of this non-sharp inequality. So if f of E is equal to f of E2, of course, we also have that f of E1 is less or equal to f of E2. So we have the injectivity as claimed. And now to see that the condition on the right is stricter, it's a stronger assumption than M. Well, let's see that we have as implication. Of course, every edge is a path, So we have empirical implication for edges, but for edges, writing that E1 is less or equal than E2, it simply means E1 is equal to E2. Because the only way in which one edge can be an extension of the other edge is that it's equal to it. Okay, so you see that the right-hand side condition is a proper. Well, I don't say generalization, is a stronger condition than our M condition. Okay, and now by discussing examples, I want you to appreciate that M condition was the right choice for our theory. Well, you proved that our proposition. And so let's do these examples. Okay. So here as our graph E, we take just one loop graph. So I have one vertex V and I have one edge E. And F, one vertex, not a single edge. Well, then obviously the map F, or if you want F bar, which goes from FP bar to FP F bar. Of course, FP F bar is equal to FPF. Because you don't have any edges. Must be a constant because it's a 1-point set, right? We have no choice. Right, but it satisfies the assumptions of our proposition. But it satisfies let me say our proposition. It doesn't make sense to write a number. You know, the proposition I proved a week ago. And this is because there is only one vertex and only one edge. Oh, I'm sorry. Well, why does it suffice? Because our assumptions are injectivity assumptions. We say that we must be injective on vertices. So of course you must be injective from a one element set. And then we say that we must have this M condition satisfied. But if you have only one edge, then obviously any two edges are equal to each other. So E1 equal to E2 must be satisfied because there's only one edge, okay? So the assumptions of our proposition are satisfied because there's only one vertex and only one edge. And this is, of course, as if it is a trivial example, but it's interesting because I must admit that I would always assume that I'm mapping edges to paths that are longer than one. But here's an example that nobody can stop you from mapping an edge into a vertex, and it works. And in fact, you do induce a very nice homomorphism of algebras, which has a nice interpretation. I described to you this example in passing some weeks ago when I was lecturing on the super duper electronic digital blackboard, but this example, in my opinion, deserves enough attention to write down the details. Okay, so let me continue. So hence, because proposition works, hence we have a unit of algebra homomorphism. which we denoted by F star C. Let me write it on another page. F star C, C for con, which maps an element in the conpath algebra of the graph E. So I denoted as a class of some chi E to FC star, the class of chi E, which is by definition here, by how we defined it. In general, this is just chi of FE, but chi of FE is of course just chi of V, which is 1. Okay, so this is simply 1 in this algebra, the conpath algebra of this trivial graph F, which is of course just the ground field. Okay, so in other words, it's a character. An algebra homomorphism into a ground field is called a character. And after identifying this conpath algebra with Laurent polynomials, sorry, no, these are not Laurent polynomials, it's the Teplitz algebra. With the polynomial Teplitz algebra, I'll identify CKE with the polynomial Teplitz algebra. Which is given how? I take the free unital algebra into generators, S star, and I divide by the ideal generated by S star S minus 1. So if you want, it's the algebra generated by the universal isometry. The only thing that is satisfied is that S star S is equal to 1. And once you complete it in a C star norm, then it becomes the famous Teplitz C star algebra. Okay. So after identifying this conpath algebra with the polynomial Teplitz algebra, which we can do by mapping in the obvious manner the class of chi E to S and the class of chi E star to S star. Okay. We see that this map F star C is simply the evaluation at 1, which means that when we have any polynomial in S and the star, what happens is for both S and the star, you plug in 1. Okay, so evaluation at 1 of S is equal to so I take any polynomial. Sorry, let me erase it. I take an element in my algebra, so this is some polynomial in S star. And by definition, this is just this polynomial with 1 plugged in for S and 1 plugged in for S star. Right, this is obviously what happens here, because you see that chi is sent to 1, and because chi is sent to S, then obviously it's the same as sending S to 1, and the same story for the stars. Okay. I didn't have to write here what happens for chi E star because it's determined by what happens for chi E. And here, well, there is simply no difference because f of E is equal to f of E star because this is just a vertex. The vertex star is just the same vertex. Okay, so I hope this is clear. And what else I wanted to comment based on this example? Yes. Okay. So this example is also nice to show the inequivalence of our assumptions. So I can now verify, well, yeah, actually, yes. So another comment for this example is that we can also see on this example, we can also see that the right, the injectivity, well, now let me, the right assumption, rightmost assumption, which we started from, is stronger than M, because it doesn't hold in this example. Whereas M assumption does. Right, I take f of E, and this is of course equal to V. V is less than equal than V, but this is also the same as FV, right? So I have f of E is less than equal than FV, but it is not true. It does not imply, well, maybe let me write it like this. So the hypothesis of implication is satisfied by the conclusion is false. Namely, E is not less than equal than V, right? An edge cannot be contained in a vertex. So sorry, not. Yeah. So I have my assumption true and my conclusion false. So it means that the implication is false. Okay. So the VM assumption is strictly weaker than the rightmost assumption we discussed earlier. And this is good that this example wasn't dumped, because this is a very, very natural example. You just take your Tepes algebra, you map it by the simple map to the circle algebra, and you evaluate the circle algebra at 1 on a circle. So this is a very, very natural map. I mean, this, you might laugh at that this is such a simple construction. I'm just writing a few symbols and then I mumble something about sister completion, but believe it or not, using pointed Tepes algebra, so exactly the Tepes algebra where you fool around by removing one point from a boundary circle, was used by Joachim Kunz to prove the theorem of eccentric, about periodicity. So these are essential tools of modern mathematics. So we don't want to dump such examples. There would be something wrong with our assumptions if they would throw aboard examples that are so simple and so natural. So we are happy that it works. Okay, now let's go to another example. Let's see now that assuming injectivity on edges is not enough. Okay, so here we prove that the rightmost assumption is too much, but now I want to prove that the leftmost assumption is too little. So let's consider another example. Now maybe let's do it on the next page. Why bother with cluttering the screen? You have unlimited amount of paper. Oops, I cannot write with the eraser. Cool. So now it's a very simple Hawaiian earring. And so I have one vertex and two edges, say E1 and E2. And F is just one book graph. So I have one vertex V and one edge E. And now I define the path homomorphism in the following way. So that the path homomorphism of graphs given by the formulas F of E2 is equal to E1, and f of E1 is equal to V. In other words, I'm shrinking E2 to E, well, or mapping E2 to E and shrinking E1 into V. And of course, V goes to D. So when we know it on generators, we know that. Sorry, I didn't finish it. V. Okay. And this is a path homomorphism of graphs because the endpoints are respected. I mean, here's just one endpoint, so everything works very easy. Okay. And now you can see, obviously, so clearly, we have injectivity on edges. Because when we have E1 different from E2, this implies that f of E1 is different from f of E2. We have only two edges and they are mapped to different paths. Okay, so we are injective on edges. However, look, this doesn't suffice because the map FC star is not well defined. So, however, let's see from CKE to CKF is not well defined. Because, and now let me compute. If I take FC of 0, FC star of 0, and it's obviously 0, and I'll write 0 in this funny way. I'll write it as I star times I. Right, this is by the first Kunst-Trigger relation, this is 0. Okay, because E1 is different from E2. So these two guys multiply to 0. F of 0 must be 0. I mean, F star C of 0 must be 0. But now we continue this calculation. And we figure out what it is. So obviously, what we will get is nothing but, well, first, to apply the definition, we have to multiply it out. So I have a class of chi of F bar of E2 star 1. Just by the definition of F star C. And now writing it out, we obtain the class of chi of FE2 star times the class of chi of FE1 without star. Okay, but now look here, the injectivity is not good enough because FE1 is V. So this is, well, I didn't even have to split it into classes, so, but let me continue. F2 star times V. F2 star, what is F2 star? F of E2 is E, so this is E star. Of chi of E star, and of course, V is the end and the beginning of everything because it's the only vertex. So V is absorbed into E star. So it's just chi of E star, which is not 0. By the corollary, remember we had this corollary that whenever you have chi labeled by only starred, only unstarred paths, then these guys are parts of the basis. So elements of a basis cannot be equal to 0. And that's it. So this is 0 is not equal to 0. So this means this is not well defined. So consequently, our proposition we conclude that the injectivity on edges does not imply M. Because if it did, this F star C would be well defined. Well, of course, we can also do it in a straightforward manner, and see that the injectivity doesn't, sorry, that the VM condition doesn't hold. We take what? We take two different edges. Say we have FE1. This is equal to V, and this is less than equal to E, right? Because V is a subpath of E. It's the beginning of E, but this is F of E2. So this inequality for the values of F is true, but this does not imply. So, okay, and at the same time, E1 is not equal to E2, okay? So I can also see it without any proposition, but I wanted to somehow show you that indeed, if we just assume injectivity on edges, that's not good enough. Such a map, as we try to write it down, does not exist, okay? All right, so let me do one more example, which also serves to exemplify something, but something else. I forgot what, we'll find out. First, let's write an example. Okay, so this time, our graph E has two vertices for a change and two edges. Oh, sorry, I overshoot it. Oh. No, not sleeping at all, or sleeping only 1 hour before your lecture is not a very good idea. But if you had to choose between sleeping or proving the theorem, of course, you choose proving the theorem. Okay, and F. Well, this is a Tapis graph. So again, we have two vertices, V and W, and two edges. This time I'll label it E and G. Okay, so the path of graphs is given by the formulas. F of E1 is equal to, oops, sorry, to G. I said G of E. And okay, by definition. And F of E2 is equal to EG. So first I walk around the loop and then I go out. Okay, so you see it makes sense because the beginning of, and of course we are identity, okay, so and identity on vertices. So F of V is V, F of W is W. Okay, so we are bijective on vertices, and our map preserves the ends and the beginnings. Right, F of E1 is G, the beginning of G is V, and the beginning of E1 is also V, works. The end of G is W, and the end of E1 is also W, check. The beginning of E2 is V, and the beginning of F of E2, which is EG, is again V, check. The end of E2 is W, and the end of F of E2 is the end of EG, which is the end of G, is again W, check. So this is indeed a path homomorphism of graphs, okay? And now, yes, okay, so I know what it is going to say. So this is a morphism in MIPG, so it is a morphism IPG, in fact, VPG. But I don't care about this. So it works for, of course, it satisfies the assumptions of our lemma. So we have a map given by this path homomorphism of graphs. It induces a homomorphism of algebras, of path algebras. And let's see that indeed we have it satisfied. Well, there's only one non-trivial case, namely f of E1, f of E2. And if you look at f of E2, it's obvious by definition that you have f of E1 is less than equal than f of E2, and it's not true the other way around. F of E1 is less than equal than f of E2. And that's the only non-trivial case, all right? Because I can take, of course, two edges equal, but then, of course, the conclusion is trivial and it's satisfied. And then I can take two different edges. So there's only one possibility. I can write it in two ways, but one way is just false because a path of length 2 cannot be a subpath of a path of length 1. So I can only have f of E1 less or equal than f of E2. This holds indeed, but does it imply, wait. I'm now confused myself. I say that it's a morphism in MIPG, but now I don't see it. Because it should imply that E1 is equal to E2, which is not true. So I'm afraid I screwed up this example. No, wait. So here, yes, okay. No, the example is correct. You see, I already told you that it's very important what this inequality means. It means that f of E1 is a subpath of f of E2 in the following sense, that f of E2 is equal f of E1 times some gamma, okay? So you must extend from left to right by a path. And of course, if I extend G by whatever, this will not be EG, all right? Because whatever extension I take of f of E1, the first edge will be G, whereas for f of E2, the first edge is E, and G is not E, so this is impossible. And if you try the other way around, it's obviously also impossible because of the length considerations. So this means that the hypothesis of implication is always false. So this means the implication always holds, okay? So luckily this was a good example. I'm just too sleepy to see it right away. Do you agree with me? Okay. So it does satisfy the M condition. Of course, it's injective even bijective on vertices, but the extended morphism fails it. So if I take f bar of E1 star, then of course this is equal to f of E1 star. This is equal to G star. And now I can extend G star by E star. So G star is less than equal than G star E star. You see, it makes sense because by G star I go from W to V, and by E star I go from V to V. So they concatenate. But this is equal to EG star, which is f of E2 star, which is f bar of E2 star. Okay, so I have that f bar of E1 star is less than equal than f bar of E2 star. Okay, so if the M condition were to satisfy, I would have to have E1 star is equal to E2 star, but it's the same as E1 equal to E2, which is not true. And E1 star is not equal to E2 star. So f bar is not in M IPG. Okay, so this is what I was telling you when proving, well, actually when we were formulating assumptions of this proposition that Niklas was proving, why I decided to skip this M condition, because I cannot extend it to extended graphs. If the M condition holds for F, it does not need to hold for F bar. This is a counterexample. Luckily, we didn't need it in our proposition, okay? But this is a step which I had thought would be taken, but we cannot take it because it's false. And I repeat, luckily it doesn't matter. Okay, so here you have three very simple examples, but they somehow, I hope, convince you that our assumptions hold water, that we are making reasonable assumptions and creating reasonable theory. Okay, so now I think it's time for the meal of the day, which is our theorem. But before I phrase the theorem, so now our goal is to extend now our goal is to extend the proposition from concav algebras let. And I say extend because every concav algebra, we know by a theorem that we proved that every concav algebra and every relative concav algebra is nothing but the Levi-Path algebra of a different graph. Okay, so if you want, concav algebras are just Levi-Path algebras of some specific graphs. Okay, and now what is, as I told you already at the beginning of this lecture, what is most difficult in proving this theorem is to decide on your assumptions. And we will need a certain definition to begin with, and it will require defining a new category. So let me do it. Let's R for regular, R MIPG. So it's path homomorphism of graphs, which is injective on vertices, satisfies this M condition. To be honest, I forgot what M stands for. I just forgot it. And R is for regularity. So let R MIPG be the subcategory of MIPG obtained by restricting its morphisms objects are the same, all graphs. But we restrict morphisms to match satisfying the following regularity conditions. Now let me go to the next page and write it as a definition. I will define the regularity condition for any path homomorphism of graphs. Okay, so it's not something that works only for injective path homomorphism of graphs. Because injectivity is irrelevant. We just combine the two conditions. M is also irrelevant. So if you want, I'm taking my most general category, where morphism are just path homomorphism of graphs, and I keep on restricting them. First injectivity on vertices, then VM condition, and now regularity condition. And this regularity condition is the toughest to come by. This is the most non-obvious condition. And just as injectivity on vertices was necessary for the covariance of the path algebra construction, when VM condition was needed to have a covariance of a con-path algebra construction. So we had to take care of one Konz-Krieger relation. Now we have to take care also of the second type Konz-Krieger relation, which is most cumbersome. And this requires, well, a fine-tuned condition, and that's the regularity condition. Because the second Konz-Krieger relation happens only at regular vertices, when's the name? Okay, so now bear with me because this is a long definition. It takes much of the page. But maybe I will first explain to you what it is I want. Yeah, before writing it formally, let me explain the idea. You see, if you would look just at the textbook, Leavitt path algebras, then you have such a theorem, but it is under much stronger assumptions. So for starters, you have really graph homomorphisms, not path homomorphism of graphs, graph homomorphisms. So edges go to edges, okay? And this already simplifies a lot. And you just say the following thing: the regularity condition is very simple. That if you have this map from homomorphism, and now you see what happens at the regular vertex of E. What you do, you restrict, right? So as a theoretical map, this is a map from FPE to FPF. Okay, and now we say, aha. So when I restrict my map, so for any V, when I restrict my map F to the set of all edges emitted at V, so SP inverse. When I restrict it, this is bijective on its image. So it's bijective, let me write like this. Okay, actually it's more, it's bijective onto SF inverse of F of V. Right, then we're home and dry because we're looking at the sum, take all edges E running the pre-image of V under SE, E star, right? Then we apply our F, we get the sum over E running this set, and we have here FE, FE star. Well, but because we have this bijectivity assumption, I can as well write down that this is the same as the sum over all edges F running, no, let me write X, F is already there. All edges X in the pre-image under SF of F of V, and X. And this is obviously nothing but F of V, and we are done. Okay, so that's what you have in this Leavitt path algebra textbook, and this is very simple. And now the problem is how to generalize it in the sort of most optimal way when your map does not preserve a length. Okay, where you have path homomorphism of graphs. What is sort of a minimal assumption to make these calculations possible? And well, informally speaking, the answer is following. So let me now answer by pictures, and then we will go back to writing down formally, rigorously, the definition. So you see, imagine that you have the following situation. You have this vertex f of v, okay, and it emits some edges. Of course, it must be a regular vertex. This goes without saying. It emits some edges. But nobody told you that you must map edges to edges. Now we're in this more general situation. Of course, I have to map edges emitted at V to edges emitted to paths emitted at F of V. This goes without saying. But paths starting at F of V need not be edges. So what we can do is the following. We take the set of all edges emitted at F of V, and then some of them we keep, and some of them we extend. But what is important, we must extend them by all possible edges that begin at this vertex, which ends the edge that we chose not to pick. Okay, this must be all. This is essential. But then again, we can continue. Nobody says that we have to finish with paths of length 2. We can keep some paths of length 2. Okay, remember, all paths must start at F of V. Let's say some other paths of length 2 we extend, but again we have to extend by all possible edges coming from the end vertices. Okay, and we continue, we go on and on and on until we get bored. And then what we get, of course, it goes without saying that we must have we must map edges that are emitted at V to paths that are emitted at F of V and that go only through regular vertices. Or to be more precise, every edge of a path which is in the image of F, when restricted to the set of edges emitted from V, must have a property that each of these edges starts at the regular vertex. Okay. So I'm having some edge E, and I map it to some path P. Okay, path P consists of some edges in F. So I have F. So I have x1 dot xn. Okay. So what is important is that the beginnings of all these x's are regular. Otherwise, we would have no hope for any calculations. We wouldn't have sums that fold up. So these two things were obvious from the start, that you must have it. But to be honest, this condition which I just showed to you eluded me for many hours, but now I think it works, and I think I have a complete and rigorous proof. So now you see, I have to somehow formalize this condition and write it down, not using pictures or examples. But that's the idea. That's the gist of our assumption. So it's very important that you have this mental picture, otherwise it's tough to follow all this notation which I have to use to write it down rigorously. Have you got any questions concerning this? Okay. Well, if not, I can just now come back to the previous board and write down the definition. So let be a path homomorphism of graphs. We call it regular whenever the following two conditions hold. So first condition is this tough one. Okay, let me write it down. So for any V, which is a regular vertex in E, the vertex F of V emits as many paths as there are edges emitted by V, but not exactly, at least as many. So as inverse V many positive length paths, so I don't want them to be vertices. Positive length paths. Let me name them P1 dot P and V, because this number n depends on V. Okay, it's just defined if you want like this. NV is by definition the number of edges emitted at V. Okay. So I still want the bijection, right? I still want the bijection when I restrict myself to this set, okay? But now I don't want to say that I have a bijection on an analogous set on the right-hand side. No, I want to pick up some subset of paths that start at the level of V and pass only through regular vertices, okay? And also I admit loops. This is completely all right. And I never told you that these P's are not loops. I don't have a requirement that edges must not repeat and so on and so forth. But that's actually what creates some difficulties. At least it created some difficulties for me. So I drew this picture, you know, like this, but this is just an analogy. I mean, I might as well say, all right, one of the edges by which I extend is a loop. This is perfectly all right. You see, what was a stumbling block for me is that I wanted to filter the situation somehow by vertices, and I couldn't figure it out. I couldn't partition the set because, of course, when you take all these paths that are on the right-hand side, which are in the image of edges on the left-hand side, then of course these are finitely many paths, so that they involve only finitely many vertices. You can bundle them together, give it a name, and so on and so forth. And then I somehow wanted to stratify this set, to filter it, but I couldn't, because I cannot say, well, this is a vertex at which only the last edge begins, but the penultimate doesn't. You cannot say it because this vertex has more role, right? I can, you know, this can be loop. I can extend it further. I can have a loop and not a loop, and it's really hard to say that a given vertex is at some given level in my hierarchy of paths emitted at V. And then I realized that the right way to filter it is by the length of a path. This is uniquely given and stratifies your set of paths, regardless of whether you have loops or not. Okay. And there is absolutely, you know, no problem of having a nice homomorphism like this. You have this Hawaiian earring. So that's what you have for a famous Kunz algebra 02. And you have another one, but your map is non-trivial. You say that you can combine. I forgot the exact recipe, but you can basically have nice four paths over there. Okay, so maybe here I should have more paths, like 4. Yes. So I would have sorry, more edges. I said I have 4 edges, and here I can very easily have 4 paths. I can have E, F, E, E, F, F, and F, E. I have very easily 4 different paths, and I can map each edge into different paths, and it works. And nothing happens with vertices. I have only one vertex. So stratifying it by vertices wouldn't work. But what is very essential is that when I decide to extend my path, as I did here, I mean, both E and F got extended, I must extend it by all possible edges. So when I have E extended, it must be EF and EE. I cannot have only EF or only EE. When I say that F is also extended, yes, then I must have FF and FE. I cannot have just FF or FE. But I can also decide to extend only one guy. Say one of my paths is F, and then I can do with, say, 3. Sorry, this was too much. With 3 edges, okay? And one edge goes to F, one goes to F, one goes to E. That's quite all right. It works. This is this choice I'm making. I keep some edges emitted from F of V, and some other I extend. So here I keep my F, but I extend my E. But well, I will emphasize, when I extend, I must extend it by all edges that come at the end of E, which here means F and E. Okay. I think I can now go back to writing my assumption, my definition of regularity. Yeah, and whose for these paths whose all edges begin at regular vertices. So I don't care if the endpoint of my path is regular or not. That's quite all right. I can easily imagine that I have such a path, and here I have, say, an infinite emitter. I mean, it cannot be a sink because well, actually, it can be a sink. That's sorry, it can be a sink. Yeah. So I can. This situation is all right, and also this situation is all right, but it's a sink. So in both cases, this vertex V is not regular, and this is the end of my path V. Okay. But what is important is that this vertex is regular, where the last edge begins, and this vertex is regular, where the first edge begins. Okay. So I don't care about the regularity of the last vertex in my path, the end of the path. Well, of course, it's irrelevant because in the Kunstkrieger relations of the second type, we care about the beginnings of edges, not the ends. Okay, so whose all edges begin at regular vertices, and that was the obvious stuff, but also will require that the set, I'm going to denote as FPV, finite paths, not starting at V, actually starting at F of V, but let me see this notation. So the set of paths which I labeled above, so P1 dot up to P and V, that this set is constructed in the following way. And here, let me, I hope I erased on this page. Yes, okay. So we take an edge emitted at F of V, and we can do two things. Either, so this is what a computer would understand. It's like an algorithm. And either set it aside as a length 1 element of FPV, or extend it by all possible edges ending at x, by all edges from Tf of x. Okay, so we either keep it or we extend it by all possible edges that can extend. And then any thus obtained path of length 2 we either set aside as an element of PV, or again extend it by all possible edges. Of course, by all possible edges, I mean all edges that end at the end of this path of length 2. So if you want by all edges, maybe instead of possible by all edges emitted from its end. Well, and I think yes, then we iterate this procedure until we obtain the set FPV. FPV is a finite set, so with this procedure we keep on throwing in paths, and also, you know, due to the very nature of the graph, we might at a certain moment bump into an end, right? I mean, it's impossible to construct anything anymore. I mean, this especially easily will happen in acyclic graphs, because when you have loops, you have infinitely many paths, so it's easier to get around. But it might easily happen that you have an acyclic graph and simply your whole space FP of finite paths is finite, so you cannot go too far. Okay, so this is my regularity condition number 1, and now my regularity condition number 2 is actually very simple. That's just a bijectivity condition. So again, for any regular vertex map F, when restricted to the set of edges emitted at V, is a bijection onto FP. So if you want, this is the obvious remnant of a classical condition that you find in the textbook. Of course, we must have bijectivity. The two sums must be equal. Something would go wrong if we had a different number of elements, although we're adding projections, but still, I don't see how to make it work without this being bijective. We'll use this bijectivity at a certain moment. Now our, if you want, input is at condition number 1. This is oops, let me also clear. Yeah, so this condition number 1. So this condition, wow, it took me 2 pages to write this condition. that's something that is non-existent before. I mean, it has only one step, right? It says, okay, take FV and take all edges emitted at FV. And then we set nothing aside. That's it. We have only paths of length 1. Yeah, and then we have to have bijectivity. But it's of course important is that we have to take all these edges. Right? We cannot skip any of them. We either set it aside or we extend. But here, as you can see, the upshot is that the number of edges emitted at f of v might be smaller than the number of edges emitted at v, but it cannot be bigger. If it were bigger, we wouldn't have a bijection. Okay, so this is like an immediate corollary from this condition, right? So if you want to have some homomorphism between Leavitt-Pav algebras, you cannot have a situation in which you have a regular vertex which emits one edge, and you map it to a regular vertex which emits 2 edges. No, this wouldn't work. Okay, because you must take all these edges emitted from f of v. So this is your v, this is your f of v. Okay. And either you just take this edge or you extend it. If you extend it, you can, well, you still have at least one path. You can have more, but you can have one. But obviously, the number of paths which we have in our construction is at least 2. So there is no way to have a bijection between one element set and the set which has at least 2 elements. Okay, it just occurred. All right. So I think we are done with the definition. This is what I mean by regularity. I can also add that the category will be instead of I. So now defining Rn dPg as the intersection of Rn IPG dPg we are ready to prove the covariance, to prove the covariant functoriality, to be precise, to prove the covariant functoriality. Of the length okay. Let me write the theorem. As I mentioned, this is a new result proved for you just a few hours ago. On the formulation of the theorem, there's no surprise. And basically, by my explanation of this regularity condition, you see how the proof is going to run. So there is not much to do in the very proof itself. However, I mean, you must do it. It's not at all so easy to write it down. It takes about 1 page in LaTeX to write it down. You have to do this calculation very carefully. and you have to study a number of special cases to get some intuition. But now it's basically down the hill. Now that we figured out what the regularity assumption should be, it's down the hill. It's quite algorithmic from now on how to proceed. But proceeding along these algorithms, along these plug and play definitions, allows you to understand them, allows you to see what they are really doing. Okay, so we are going to do it step by step. Okay, but let's first write the theorem. So the assignment, and this is, I formulated in exactly the same way as the proposition we can go. Okay, so there's no surprise. So the assignment. Objects in my category R and IPG, so all graphs. Any graph associates related graph algebra, which is a unit of algebra over so an element, an object in the category Ka. Okay, and of course the interesting part is with morphisms, but I define it in a completely analogous way as I did it for the compact algebras. I take a map, I take a path homomorphism of graphs, and I map it to a homomorphism of path algebras. I have F star L going from LKE to LKF, which is now a morphism in Ka, an algebra homomorphism. And well, we have an explicit formula. So for every P, which is a path in the extended graph, bar here, we have the following. We take, well, I know that an element in my Levitt path algebra has a finite linear combinations of chi p's, where p is a path, a finite path in the extended graph. Take its class to make it, to push it down to the Levitt path algebra. Okay, so this is now an element of L. All right, and I map it by this F star L to the class of chi of F star of P, which is now an element in the Levitt path algebra. Of course, you have to prove it is well defined. But the claim is that it's not only well defined, but defines a covariant functor. So the assignment, blah, 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 defines a covariant functor. Just before, in the proposition, we can also handle the unity case. So furthermore, the same assignment but restricted to the subcategory RM BPG. So now we take only graphs with finitely many vertices and morphisms that are bijective on vertices. And this defines a covariant functor category of unital algebras of Bauer field K. Okay, so this is the statement of the theorem. And I'm thinking how to proceed, because I basically, I finish now, as promised. This is 75 minutes. And now I don't know what to do. Should we do recitation classes and postpone the proof to the next week, or do we continue the proof and have huge recitation classes in a week? No, maybe let me try to improvise the recitation classes, and let's see what happens. Anyway, for the time being, I stop recording, and I'll see you at 4:15.